In this video, we're going to be talking about Charles' law. And our goals are we want to be able to describe the relationship between volume and temperature for a fixed quantity of an ideal gas at constant pressure. And then we want to be able to calculate the final volume or temperature of a gas given some initial volume or temperature. And we'll do two examples of that in this video. Okay, so here's the relationship between volume and temperature of an ideal gas. And so there's this experimental apparatus on the left where we have a thermometer that's rubber banded to this capillary tube. And in this capillary tube, there's some air trapped down here with a mercury plug on the top. And because the diameter of the capillary tube is constant, the height of this air bubble, if you will, is proportional to the volume of the gas in this capillary tube. Okay, so a student might perform this experiment, change the temperature and measure the differences in height here. And so this is kind of the table, a table of the data that a student might collect. And plotting it up on a graph, as we see here, if you plot the height, which is proportional to volume, versus the temperature, okay, in the absolute scale or the Kelvin scale, this relationship passes through the origin. And what this is saying here is that volume is directly proportional to temperature, okay? So this is an example of Charles' law, and that's an experiment we're going to be doing later in the semester, where the volume of a fixed quantity of a gas at constant pressure is directly proportional to absolute temperature. All right, so we have this V is directly proportional to T. And remembering from our lecture on proportionalities, we can turn this into an equation by inserting a proportionality constant I'll call K into the equation, where V is equal to some proportionality constant times T. And I'm going to rearrange this equation. I'm going to divide both sides by T. So it's going to look like this now. V divided by T is equal to K. Okay, some proportionality constant. So that means that the ratio of a given volume to temperature is a constant. So from this, it follows then the following equation, which I'll write as this in this form: V1 over T1 is equal to V2 over T2, which is equal to K, which means given any volume of an ideal gas at a particular temperature, that ratio should be a constant. It should be K, the proportionality constant, okay? And these subscripts, the 1 and the 2 here, okay, indicates the initial measurement and the final measurement. So V1 is the volume initially, V2 is the volume, the final volume, and same idea with temperature. T1 is the initial temperature, T2 is the final temperature. Okay, so that's what I just said. I should have maybe wrote this down here, but this is basically what we're saying here. Okay, for a fixed quantity of gas and pressure, divide both sides of the equation by T. You get what I wrote on the top. And then you could solve as I did here. All right, so let me just rewrite that very quickly just for our notes. Okay, so V over T is equal to K. Okay, there we go. That's a little bit neater. Okay, so we should be able to solve this equation for any variable. So this is an example of Charles' law. Okay, we want to be able to solve this equation for any variable. Okay, so that guy right there. And what do I mean by that? Well, we're going to do two examples in the next slide to figure that out. Okay, so here's our first example of a problem that you'll be doing for Charles' law. So it says a fixed quantity of gas in a flexible walled container is cooled from 44 degrees Celsius to 21 degrees Celsius. And the initial volume of the container is 3.2 liters. What is the final volume? Okay, so let's just begin by writing our equation. V1 over T1 is equal to V2 over T2. Okay, now let's write down on the side here what we're given and what we want. So we have V1, T1, I'll write V2 and T2. Okay, so V1, what's our initial volume? The initial volume is 3.2 liters. Okay, the initial temperature, so it's cooled from 44 degrees Celsius, so that's what we started as, to 21 degrees Celsius. And we don't know the final volume, so we don't know V2. Okay, so there's a few things that we need to do. So first, if we look at this equation, we need to get V2 by itself. We need to get the variable of V2 by itself in the equation so we could solve for V2. So what we're going to do, I'm going to just write this a little bit bigger over on the side. So V1 T1 is equal to V2 T2 is that I'm going to cross multiply. There's several different ways you could do this, and it explains a few ways in your book. So you could look at all the ways and see what you feel most comfortable with. But how I like to visualize it is I want to get V2 by itself. So the T2 needs to move. And how I'm going to move it, I'm just going to cross multiply it. Oh, I'm going to bring it up here. Okay. So move the T2 over. So when I do that, I end up with this equation. T2 times V1 over T1 is equal to V2. Okay? So that's what we have here. Again, it's V2 is equal to T1, or excuse me, T2 times V1 divided by T1. Okay, now, how do we solve the equation? Well, first, remember that the relationship between volume and temperature is for absolute temperature. So anytime you're doing a problem with Charles' law, or in a few videos, we're going to see an example of the combined gas law, you should convert all of your temperatures to Kelvin. You should just get in that habit. So we add 273 to that to convert to Kelvin. Okay. And for T1, I get 317 Kelvin. And for T2, I get 294 Kelvin. Okay. So now I'm ready to put all this in my equation. So T2 is going to be 294 Kelvin. So if you don't convert to Kelvin, you're going to get the wrong answer. Okay, so always remember that. So I have my volume, 317 Kelvin. Okay, and when I put all that in my calculator, the answer I get is 2.97 liters. Okay, so that is equal to V2. All right. So that's an example of solving for V2. So let's do an example where we're solving for T2. So a sample of gas has an initial temperature of 25 degrees Celsius and an initial volume of 1.75 liters. At what temperature will the gas have a volume of 2.52 liters? All right, so again, just so we get in the habit of seeing it and writing it down, that's supposed to be a 1. T1 is equal to V2 over T2. I'm going to write down our variables here. Okay, so V1 is 1.75 liters. Okay, it has an initial temperature of 25 degrees Celsius. And remember, I have to convert that to Kelvin. So we're just going to add 273 to that. And when I do that, I get 298. Okay. And then for V2, I get 2.52 liters. And I don't know T2, right? At what temperature? What is the final temperature? Okay, so I need to get the variable T2 by itself. So I'm going to write that kind of on this side. Let me write a little bigger. So V1 T1 V2 over T2. So I'm going to do the same approach. I'm going to, let's see here, get T2 over here, okay? So T2 V1 over T1 is equal to V2 is what I have here. All right. And then what I'm going to do is cross multiply again. So the V1 is going to go down here. The T1 is going to go up here. What I'm left with is T2 is equal to V2 T1 over V1. Okay? So I'll let you kind of look at that. Like I said, there's a few different ways you could do it. I went a little faster in this example, but you should become comfortable with this. And if you have any problems doing this sort of rearrangement with the equations, just reach out to me and I'd be happy to answer any questions and help you out. Okay, so let's plug in our variables here. So V2 is 2.52 liters times 298 Kelvin over 1.75 liters. When I put all that in my calculator, I get 429 Kelvin. Okay. So that's another example of going through Charles' law and solving for the variable T2. Okay, so you should maybe do a few examples of solving for all the variables and just rearranging this equation till you're comfortable. And in the next video, we're going to be looking at Boyle's law.